Tengo que usar mi propio.
¿Qué edita el propio computador? ¿Cómo se conecta? ¿No se puede? Ya le he preguntado. ¿Tú sí lo tienes ahí, Michael? ¿Tú lo puedes en internet? ¿O con el internet?
Puedo usarles de Google Slides.
Sí, ya, espérate.
Pero tal vez pueda. Si puedo recordar el caso.
O si me lo reenvías a mí y yo te lo
tiene videos
no
que no funcionan, pero se puede ponerlo.
Sí, espérate.
¿Ya se puede?
No.
Ok. Déjame ver si.
¿Tú tienes alguna
No.
¿Y tú me la puedes enviar a mí?
Bueno, es solo porque algunas del texto no va a funcionar.
¿Al correo?
Sí. Sí, yo puedo hacer. Pero bueno, tengo una idea. Es tu correo electrónico.
O en tu correo.
Like, can I get in here? Uh, uh, no, how do I? Lucía, Lucía, ¿cómo es el app?
¿Cómo se la roba acá? ¿Tú sabes? Ya,
Oh.
ya. Es que a veces yo utilizo Mac, entonces siempre me pasa lo mismo. ¿También?
Sí.
No.
Porque siempre ya está.
No hay conexión aquí.
¿Cuál es la clave aquí de Wi-Fi?
Necesito 2 minutos más.
I hope I have signal. Because it's only password verification. Your signal's not good enough.
It's uploading here, so
This is very slow. ¿Dónde estás? ¿Dónde está? Pero no tiene mis slides. ¿Dónde está?
pero no tengo conexión.
Okay, mine's ready. Okay.
Pues en WhatsApp y aquí me coloco rápido en WhatsApp, es más rápido.
¿O prefieres email?
No, en WhatsApp. Mándalo en WhatsApp.
Muy bien. Somos profesionales.
de pronto digamos tanto que terminen aquí, sí, pueden terminar como 15 minutos que les hace
Sí, sí,
presencia,
sí, bueno.
para terminar, porque en una cosa que son también a las 3 de la tarde.
No, sí, por eso.
Sí, entonces ellos presentan 15 minutos y los estudiantes con
Sí, listo, listo. Necesito, dice que necesito.
Ay, ay, ay.
Ah, no, pero es que.
Ok, bueno.
Sí, mandárselo a él. Vas a empezar tú. Michael, ya
Bueno.
te entonces vas a empezar tú. Y ahora sí, ya, no, lo metes. ¿Listo?
Más o menos.
Aló, aló. No sirve. Buenas tardes a todos.
Hola.
Disculpen la demora un poco, pero estamos también con el vicerrector. Entonces, para los chicos que estuvieron aquí desde las 11, les agradezco mucho que hubieran venido a las charlas de dos invitados que estuvieron con nosotros con el grupo de diversidad y equidades durante estas vacaciones. Y les voy a presentar a Clay. Clay Wall pues es un investigador y también pues, es fotógrafo. Él trabaja con fotografía y con conservación de polinizadores en Estados Unidos. Entonces él les va a contar un poco sobre lo que él hace y entonces para que
Hola a todos.
Hola.
Es un verdadero placer
hola,
presentarles hoy. Debo disculparme de antemano por mi español o spanglish y porque mis diapositivas están mayormente en inglés. También quiero agradecer sinceramente a los profesores Lucía, Víctor, Michael y Melissa por toda su ayuda durante mi estancia aquí. Y escanea este código QR para ver mis notas de cada diapositiva en español, por favor. Es mejor que mi español. Cuéntame cuando estás lista. Bueno. Okay. I am a macro photographer. As Lucia said, I'm a professional conservation photographer. I've worked for many years for many different conservation organizations around the world, including World Wildlife Fund in the United States. I've also worked for nearly 20 years as a photographer documenting insects and other small species that are in need of conservation. And of course, my specialty is photographing bees. I love bees of all kinds, particularly those native species, those species that are native to places like Colombia and many parts of the United States. I've been here for the last 2 weeks photographing the bumblebees or los abejorros de Colombia. And during this trip, I found 7 species. There are 9 species, and I was able to find 7 species in Colombia, which is Colombia is an interesting place for bumblebees because mostly bumblebees live in places in the world that are colder. But of course, here in Bogota, there are many species and many high altitude places where bumblebees can live. Here are a few of my favorite photographs that I've taken during this trip. This is one of my favorite species. This is Bombus excellens, which is a really beautiful species of bumblebee. Also, anyway, and also because also love the Amazonian bumblebee. This was one that I photographed in Chimesa visiting Lulo. And of course, Bombus rubicundus, which is living high in the Paramo. So as a photographer, when I'm teaching people about photography, there are some questions that I like to ask people. What is your goal? What is your meta when you're trying to figure out how to approach photography? And there's two questions. Do you want to simply document your subject? You know, just take a record shot? Or do you want to tell a story? Do you want to communicate about the subject? Or do you want to do both?
Sí.
And those questions help you to determine which type of equipment you want to buy. So there's a couple of options. You can either go with your trusty cell phone, which has a camera, or you can get a more professional camera. And both options have pluses and minuses. So with a camera, there's some great tips. For example, you always have your cell phone with you. It's always in your bolsilla. And you can shoot, high res and raw files on a cell phone these days, especially with iPhone and other types of cameras. And new phones have improved macro capabilities. The cons are slow response time, true flash is not an option, there's poor native magnification, and it's a phone, so it's not a camera. However, for your cell phones, you can get attachments that help with taking macro photographs. So Sandmark is one of the brands that you can get that can give you 10 times life-size magnification on your smartphone. So if you look on Amazon, you can find lots of different options, but there are some pretty neat options that you can get for your cell phone. However, well, and this is an example. So it's pretty good. It's better than what your cell phone can do, but it's not exactly, great. But some people are taking it too far with their cell phones. At this point, you should just buy a camera, right? Like using your cell phone is not going to work. For a DSLR or a mirrorless camera, there are a lot of pros. It's made for the job, so you can make really good photographs. There are many different types of macro lenses that are available. You can use fast shutter speed, which is really helpful for when you're trying to photograph insects in flight. And high-speed flash allows you to capture that motion better. The cons are they can be expensive, they're very heavy, hard to carry, and there is a learning curve as well when you're trying to use a DSLR. But if you're serious about photography, it's better to go this route. The other thing I'll mention is that you don't have to have the most expensive camera. Cameras can be very, very expensive, right? It's more important to have good quality lenses than the camera itself because, I've been working in photography for over 20 years and the oldest cameras can still make really good pictures. So it's not important to have the newest camera. So I have some simple tips to help you improve your photography if you're interested in photographing really anything, but specifically about insects and small creatures. The number one thing is to change your perspective. This is a very simple tip, but it makes a big difference. So the first thing I like to tell people is that over 99% of life on Earth, most of life on Earth is smaller than your little finger. And because of that, if we're trying to look at animals from the perspective of being a human, a very large species, we're going to miss a lot of other things in the world. The truth is we're all giants. Everyone in this room is a giant species on our planet. There are, of course, whales and tigers and bears, species like that, but we are among the largest species on the planet. And because of that, we tend to relate to the other species that are giant like we are, but in fact, we're in the minority. So we see something going past and it looks like a small piece of dirt or dust, and we don't have the ability to see it with our own eyes. But when you look at it up close, it's incredible. It's like a living jewel. And that's what photography can do, not only for you, but for your audience when you're trying to communicate the importance of small species that need protection. And have you ever seen people walking around with their iPhone or their iPad trying to take photographs of insects on the ground like this? And they wonder why the insects fly away? Why they're afraid? Well, it's because we are these giant animals walking around. When imagine if you're an insect, right? What's happening here? Oh boy. I don't know what's happening. Okay. The camera the computer malfunctioned because it was too horrible. Okay. Sorry. I ruined my own joke. Okay, here we go again. So imagine you're an insect and you see that, right? That's like terrible, right? So why were they going to fly away? Because you're this giant creature. So if you get on the level of your subject and you look them in the eyes, you make a connection with your subject, right? And that's what you want to do. Not only do you make a better photograph, but you can see when the subject sees you. So you're having this give and take, and your opportunity for making a photo increases. And I call this eye candy. It's like when you're able to like really look in their eyes, you make a photo that's very pleasing to the eye. So humans are very social creatures, right? And because of that, we focus on the eyes of our subjects. So you can't imagine taking a photograph of a capuchin monkey without getting the eyes in focus. And the same goes for other species, even species that people, may not necessarily connect with. So if the eyes are in focus and nothing else is in focus, the photo still works because we are visual creatures. It works with other species too that maybe people are not necessarily used to connecting to. Snakes, for example, it creates a connection with your subject. Another important tip, and many of you probably are biologists in this room, but it's to play biologist. Because if you understand the behavior of your subjects, it increases your opportunity to capture unique behavior and make a better photograph. Anybody can go out and snap a photograph and move on their way, but really good photographs focus on the behavior of your subjects. So for example, in the state that I was born in, South Carolina, there's a species of ant who herds aphids in the same way that we work with cattle. And I had read a lot about the biology of this subject, so I knew what time of year to go to look for the subject, how to photograph it, those kinds of things. It increases your chances. Oh boy, not important. So for example, this is a leafcutter bee. And this is a female leafcutter bee going back to her nest with a piece of leaf. And because I knew what to look for, I was able to find her and photograph her. So a lot of people have questions. What is macro photography? I'm a macro photographer. What is macro photography? And it's a little bit complicated. So the best way I can describe this is that because I'm old, I think about slide film. And if I had an actual tiger beetle next to that slide, if the image on the slide was half size of the living species, that's called close-up photography. If the insect is the same size as the insect on the slide, that's true macro photography. So that's called 1:1 or 1x. If it's beyond that, pretend that there's something here. If it's beyond that, then it's ultra macro. So that's anywhere from 3x or 4x up to 6x. So there's some tips that will help you be a better macro photographer. One thing is, if this is your camera and my subject is here, you want to keep the back of the camera parallel with your subject because that allows more of the subject to be in focus. I also always use manual focus with my photography because insects move very quickly and the camera cannot keep up with it. So instead, I'm looking through the viewfinder, I'm moving my body in to make it in focus versus letting the lens do the work. If you're on the ground and you're having a hard time keeping the subject in focus, bag like this, and it helps it to stay steady. And then again, always look at the behavior of your subject to make sure that it's it's comfortable, that it's relaxed, because you're going to get better photographs that way. Another thing to consider is the type of lens that you're buying. There are two different options. There's prime, which is a fixed magnification, and there's a zoom lens, which can give you a lot of different kinds of magnifications. And there are advantages to both. Prime is better because it's made for that job, and it's going to have less glass within the lens, so it means it'll be sharper and more in focus. The next thing is what's called working distance. That's the distance between your lens and the insect itself. And that's important because if you don't want to be photographing an insect from like the other side of the room, right? So the closer you are, the better the photograph will be. And here's some options. So this is a lens that I really like. It's a Tokina 100 2.8, and it says macro here, but it's not really a macro. It's a close-up lens. And that gives you images similar to this. So it'll give you magnification similar to this. Again, that photo was made with this. So this gives you a sense of the kind of magnification you can get at close-up magnification. For true macro, this is a really good lens. I love it. It's not too expensive. It's a 100 millimeter lens that will allow you to make up to 2 times life-size magnification. So you can start making photographs like this. This mason bee, this bumblebee, you can kind of get a sense larger in the frame, or this leafcutter bee. So pretty good magnification. For ultra macro, this is a really cool lens. It's a little bit difficult to use, but it's also by a company called Laowa. And that will allow you to do so this is a very small bee, but it allows you to make photos that are quite large with this insect. Even small things like springtails, which are really, really small, you can photograph them with this lens. Another technique that I really love is called close wide or wide angle macro. And this is a technique that I'm a little bit more well known for because it allows you to show both the subject and the environment. And this is a lens that I use for that. You can buy this lens used for pretty reasonably online. It's a Sigma 15 millimeter diagonal fisheye lens. It's a corrected fisheye. So to give you an example of the difference, this is kind of a traditional photograph of a snake. And to me, it's not a very good photo. It's a pretty boring photograph because the subject is, you don't really learn much about it. It's just kind of like, oh, it's a snake. But by using this close wide technique, you totally change the context. So you can see the subject, you can see the background, you can tell a story with a photograph. Here's another example. I love this technique because you can see the insect and you can see where the insect lives. Here's another example. This is in Alaska in Denali National Park. So this looks like the flowers are huge and the bumblebee's huge, but in fact, it's really small. So to show you how this lens works, this is a picture of me taking a photograph. So the flowers are very small. You know, everything's miniature, but it looks very big on the image. Here's another one of my favorites. This is the bumblebee in front of the Golden Gate Bridge in San Francisco. So it tells a story, and that's why I love this technique. So it's just one of my favorite ways of photographing insects. And it's also really important for conservation. This is a really rare toad in Panama. And when I took this photograph, this was the only place this toad was found. It was very close to extinction. And so I was able to show the subject and where it lived to help tell a story to help protect the species. So a few tips for success. Always look at the sky because you want to be able to see into the distance in your photograph. One of the things that I also like to do is test the exposure of the photograph on a plant before I actually find the subject, because if I'm in a field, I'm often chasing the subject and I don't have time to set my exposure. Also, you always want to be looking at the direction of the sunlight to make sure your flash matches that, and it helps to be able to see into the distance to help this work. There are also some really strange macro lenses. This is a probe lens. There's a bunch of different kinds made by this company, Laowa, but I wanted to take a photograph inside of a bumblebee nest in a log. And so I was at Sean Steffen's house actually in Wisconsin, Michael, and we'd set up a colony inside of a log, and there were some holes. And so this is how I took the photograph. And I have all of this because I was afraid that the bees were going to attack me. But it's really a cool way to take photographs. The other thing that I want to share with you sort of towards the end of this is that flash is super important. When I first began doing photography, I was afraid of flash because it's complicated. I didn't think it was natural and those kinds of things, but it makes a huge difference. So like my early photographs are like this, where very little is in focus. It's beautiful, but it's just very limiting in terms of what you can do. Flash allows you to shoot during all times of the day. It helps you freeze motion. It's great. And when you're trying to photograph something in the early morning when the sun comes up and the plants start moving without flash, it's very difficult. This is like 20 years ago. Also in the middle of the day when there's really bright reflections and there's lots of shadows, flash can help fix that. So here's an example. And this is called fill flash. Fill flash is basically when you just have a very quick burst of flash that helps to fill in the shadows in your photograph. So this bee was backlit. The sun was behind the bee, and it would have been completely dark in the foreground without this fill flash. This is an orchid bee from Tatama National Park in Risaralda. And again, the subject would have been black and dark without the flash, but it makes a huge difference when you can use flash. And those short bursts of flash freeze motion. So this bumblebee was flying into the sun, but by using fill flash, suddenly it's in focus. Same thing here, bee flying in a storm, very dramatic. The flash helps to freeze the motion. Another thing that I love to do is backlighting. So I love to have the sun on the other side of the sunlight because it gives you this beautiful effect around the edge, this rim lighting, and then a little bit of fill flash balances out the shadows. Here's an example of how this works. So I was in South Dakota in the United States, and there were these small male mining bees on a plant. And this is a pretty boring photograph. The sky is gray. The wind was blowing, and I was facing east. So I turned around the other direction, facing west with the sunset. And with fill flash, I was able to make a very different photograph just by turning around. So just a few tips for flash very quickly. Think about flash like a recipe. You start with your first ingredient, which is the natural light, the light of the sun. You set your exposure to that. And then you add in flash as you need it. It's like you start with your broth when you're making a soup, and then you add in your vegetables. Ideally, you don't put it all in at the same time unless me, and I'm not a great cook. So the other thing that's really important is to hide your flash unless it's meant to be seen. Typically, as a photographer, you don't want the audience to see the flash because you don't want them to think, oh, a photographer took this picture. You want the viewer to look at the subject and go into the scene in their imagination. And then the other thing that's very simple is when you're working with a living animal, if you need to change the exposure, rather than messing around with your camera, just move away. Move the light further away from the subject, and that will make the light smoother on your subject. It's faster and easier. So just to give you a quick example, I was in Panama photographing a leaf mimic katydid. So the first thing I did was set my exposure. So I'm looking at the natural light. I set that. And now I'm going to begin to add in flash. So start with flash, and it's better. With flash, it's better. But it's still a little bit harsh. It doesn't look natural. So by moving a flash further away, balancing my light more, now I make a picture that looks more natural, like I'm in the forest. And no longer as a viewer am I thinking about the fact that this is a photograph. I'm in the moment. The other thing that's really important, and this is my last tip, is if you're using flash, use a diffuser. A diffuser is very, very helpful to making the light very soft on your subjects. And this is an example of kind of how I would do that, right? So I've got my flash off camera. I've got a diffuser, which makes the light very soft, and I can move my flash away from the subject as I need to. And there's a little rusty patched bumblebee right here on the plant. There are a lot of different kind of diffusers you can get online. They all work in different ways. But the one I've been using most often is this design, which allows you to keep the flash on the camera. It looks crazy, but it works super well. And they're not too expensive. And you can even make your own. And that works like this. So really nice, soft light on your subject. It looks very dreamy. I love this, the way this looks. It's been a game changer. And it works with lots of different species of very, very tiny insects. And if you don't have money, there are a lot of options online where you can basically just use garbage to make your diffuser. In fact, this photograph, I used trash to make my diffuser. It was in Colombia. I didn't have anything, so I just used styrofoam and cardboard and stuff, and it worked great. And I probably won more awards for this photograph than any other photographs. So that's my talk. Thank you so much.
Existe como una influencia o que haya como una distorsión de la imagen, digamos, cuando uno toma la foto a mediodía, cuando se trata de un tiempo con fotógrafos de macro, que decían la peor hora para uno salir a fotografiar, lo que sea, es al mediodía, y hay forma de cómo contrarrestar ese efecto.
Durante el mediodía, uno de las luces más fuerte. Oh, no, en línea. Ok, hay algo con, no sé cómo se dice en español, high speed flash. Y es una manera que es algo que tú puedes cambiar dentro de tu cámara y tú puedes usar el flash con todos los shutter speeds. Pero necesito cambiar dentro.
Silencio, por favor.
High speed flash. Sí, porque en línea no puedes ir pasado más 250, 250 en el flash.
Ok, muchas gracias, Clay, por tu charla. Seguimos con la segunda charla con el profesor Michael Jenner. Él viene de la Universidad de Wyoming y estuvo también con nosotros estas semanas trabajando y les va a contar un poco sobre lo que él hace, sobre su trabajo con fisiología un poco y con clima.
Sí, ¿listo?
Dale.
Bueno, gracias. Primero, quiero decir gracias a Lucía y a Víctor para hacer todo esto posible, ¿no? Por el apoyo y todo eso. Entiendo un poco de español, pero no tiene las palabras para decirlo en una charla de ciencia en español. Así que, si me los permiten, voy a hablar inglés. Pero también puedo entender, así que tienes preguntas, por favor, ask me questions, yeah? I did also want to briefly just thank Victor's students and the students in Lucia's lab. It's been really fun getting to know you guys. They worked, I'm not going to show any data from when we've been here, but they worked really, really hard in the field. I think probably if they had the option to go in the field with me again, they'd say no. Because we did very long days, cold, wet conditions, but you guys were awesome and just did the work and then done a lot of work afterwards. So thank you for that. That's been really fun. So I'm going to talk a little bit about some of the work we've done with this. So Clay, I'll just ask you to close your eyes for the rest of the talk because my photos are awful after seeing Clay's photos. I think I took this with an actual, not a cell phone, because this was a long time ago. And I'm clearly not a photographer. Okay, good. So I'd like to show this picture first. So I've been studying these bees for a long time now. I'm not going to say how long because Victor will tease me about my age. This is a bumblebee, of course, abejorro, no? But I like this picture because it shows what I want to talk about. So this bee is flying. And as you may know, flight is very difficult for any animal, particularly for a small animal like this. This is in Western China. I'm going to show you a little bit of data from Western China. I spent some years working there. And we're at about 3,000 meters, so pretty high. But that's not very high for bumblebees, as I'm going to show you. They actually go very, very, very high, 5,000, maybe 5,500 meters in elevation. So you can see it's flapping its wings. You can see the sun on its back. So this, in addition to having to fly, it has to regulate temperature, right? And it has to do that in often very cold places, but it also deals with sun, which, as I'm going to talk about, could make things quite hot. And then, of course, it's got its tongue sticking out. So it has to do all of this by essentially balancing its energy requirements, right? It has to be able to feed to supply these activities. So I'm going to talk a little bit about flight in these conditions and a little about temperature, how they respond to temperature with the time that I have. So in a really simple sense, so these are mountains near where I live. These are the Tetons in Wyoming in the US. So this is the valley here, and this is at about 2,000 meters. And then the tops of those peaks are at about 3,500, 4,000 meters. So pretty high. And what's exciting to me is if you hang out in these places, when you're at the lower elevations and you move up a mountain, you as a human, as a giant animal, right? You sense the changes. You know that as you start hiking up that mountain, or in our case, running across campus to get here on time with Lucia, chasing Lucia, you can sense the low oxygen. When you go to high elevations, you can sense the cold temperatures, right? You know that, okay? So very simply, what I think a lot about is how is it that the environmental conditions that are out there challenge animals, and then how the animals respond to those challenges, physiologically mostly, okay? So in this case, I'm going to focus again on this bumblebee, partly because you find them in so many interesting environments. I'm going to talk about two main things. The first challenge I want to talk about is thin air. You get to high elevation, the air is thin, that makes it harder to fly, right? This is why it's difficult to do rescues off of Everest. Helicopters have to dump all their extra weight because it's so difficult to produce lift at high elevations. And so I'm going to show you some data that suggests actually bumblebees are kind of superheroes. So they can fly at incredibly high elevations with no problem. And then I'm going to switch to temperature and talk about this. Now, you know, as you go to these cold places, these bumblebees are, of course, experiencing cold conditions. But as many of you know, bumblebees are capable of warming themselves internally, right? So they can heat themselves up with their flight muscles. And so they may be able to counter these cold conditions just by expending energy to heat themselves. And so that may be a really good thing. But it turns out also, if they heat themselves, they can potentially overheat if conditions get temporarily hotter. Or if they live at lower elevations or in warmer places, as many of them do, deserts, transversalis down in the Amazon, this heating part that they have, we think of as an advantage, may be a disadvantage in those locations. So what I want to talk about is some of our work trying to figure out, one, what are how can they tolerate different temperatures, be they hot or cold? Is that locally adapted? And why might we care about understanding that tolerance, that temperature tolerance? So I'm going to start with the flight stuff, and I'm going to start by showing you a really complicated figure. So don't fall asleep when I show you this figure. I'm going to walk you through it. There's a lot of information bound up in this figure. So this bottom axis is air density, right? That's how thick the air is, how many molecules per unit space, right? So high air densities we find at low elevations. So what's confusing about this graph is low elevation is up here at the top right. As you move down this line, you get to higher and higher elevations. Air density falls, and the partial pressure of oxygen, or how much oxygen is available in the air, falls, okay? So as you get to high elevations, less oxygen, harder to fly, essentially, right? And then the color of the line is indicating temperatures, right? It also gets colder as you get to higher elevations. Now, just for fun, I put the tallest peaks on the different continents on there, just use some scale. And then as a kind of hobby, I like to track records of the highest insects, actual collections of insects that people have documented. And so here's our bumblebee here up around the 5,500 meters or so. Okay, so at these very high elevations, they're experiencing huge reductions in air density, huge reductions in oxygen. Okay, so what's going on there? So we know that air density challenges lift production, and reduced oxygen challenges metabolism. I think we as humans who, one, are large, and two, we walk, we don't fly, right? We don't fully understand how big of a challenge this is. So just to put this in perspective, so a flying bumblebee, just flying, compared to an Olympic sprinter. So a flying bumblebee is using about 100 times more oxygen per unit time than the fastest Olympic sprinter when they're sprinting full speed. Okay, so it's a huge challenge for a flying insect to be able to supply that oxygen when you get to high elevation. And as you'll see, we still understand how they do it. So the first question we had was very simple. We find bumblebees at these high places. Are they limited in how high they can go by this thin air that has very little oxygen in it? And so to address this question, we went to Western China. This is the center of bumblebee diversity. So in a small area in Western Sichuan, there's about over 70 plus species of bumblebees in that small area. And they do really, really well there. There's tons of them. In fact, it's very difficult to catch replicated samples of the same species because they're so diverse. So we went there, and we also have a really good gradient. We go from 500 meters elevation to over 5,000 meters elevation in about a 12-hour drive. So you can cover a huge elevation spread. So we went to Western China. We collected about 3,800 meters. This is a mountain pass. So we're looking at mountains that are about 6,000 meters high from this pass. So we collected this pass. And then with colleagues, so these are Chinese colleagues. This is Lao Guo from Sichuan University. This was many years ago. He was an undergraduate student at Sichuan University. David's now a professor back in China. He went to school at UC Berkeley and went back to China. This is Robert Dudley at UC Berkeley, my collaborator. This is our driver. When I was going to China, when you rented a car, you had to rent, somebody came with and drove you everywhere. This driver loved the science, so he would come out in the field with us and help us with the science. It was a lot of fun. So this right here is a chamber. And we can seal this chamber up, and then we can either suck air out of that chamber or add air into the chamber using a hand pump. Again, we're in the field. And then we have a video camera above the chamber that allows us to film these bees when they're flying. And so what we're doing is we're simulating movement up and down in elevation to try to figure out, can we make these bees fail? Okay, so we collect bees at 3,800 meters. We put them in the chamber. We experimentally move them down mountains and up mountains, and we ask, where do they fail, or do they fail? Okay, so when we do this, it looks something like this. This is a bee flying at the equivalent of 2,000 meters in the chamber. So you can see she's just zipping around there, no problem. This is easy. And one thing you can see, hopefully, is kind of the blur her wings make. From that, I'm going to show you we can measure this angle that they're beating their wings through. Okay, so that's one flying at 2,000 meters. Here's the same bee now at a simulated 6,000 meters elevation. First thing you're going to see is she doesn't really want to fly, right? But in a second, you're going to see her take off, and she's going to hover all of her own accord, and there she goes. So she's flying at 6,000 meters, which is pretty ridiculous, right? So just the air density challenge is about fourfold higher than flying at sea level. The oxygen challenge is ridiculous as well. So we did this for a number of bees. And what we did is we measured for these bees, what's the highest elevation, simulated elevation at which they can fly. So they are able to take off on their own. And then because sometimes bees have behavior, they choose to do things and choose not to do things, right? We also measured what's the lowest elevation at which we could measure failure. And so we basically see them trying to take off and they just can't get off the ground, okay? And then we take the midpoint between those as sort of an estimate of the maximum elevation that bee can fly, okay? So when we do that, it'll let me switch. There we go. So here's a number of bees that we did this for. So each one of these, that blue is the highest they could fly. This red is the lowest elevation at which they tried really hard to fly, but they couldn't. And so this purple is kind of our median estimate of the highest elevations they can fly. So on average, these animals can fly over 8,000 meters. So that 6,000 meters wasn't particularly high for these animals. And we had two that flew over 9,000 meters elevation equivalent, which is kind of ridiculous, right? So our answer to our first question, does thin air limit bumblebee flight? No, not really. So these animals are capable of ridiculous flight behaviors. And if you think about the amount of oxygen they're trying to supply, it's crazy. Now, are we saying, when this got picked up by like BBC and other places, oh, do you find bumblebees on Everest? No, that's not what we're saying, because this is a very short-term experiment, right? So we're not incorporating anything else about that habitat that's actually limiting them. You do not find bumblebees on Everest. I'm not aware of that. You do find them very high. So this excess capacity they have, you might ask, why do they have that? Well, as you know, bumblebees are sort of like tankers, right? So they have to go around and load up on nectar and pollen to bring it back to their colonies. Likely a lot of this excess capacity is associated with that lifting they do, and not with the altitude per se. But they're able to lift at high altitude, right? Which is pretty remarkable. So then the question is, how are they doing it? So there's a number of ways to look at this. We know from biomechanics, there are kind of two primary ways that insects can increase lift production, right? So one, you already saw that blur. They can increase what's called the stroke amplitude. So if you imagine, so bees are flying like this, right? So if you imagine changing the angle through which they beat their wings, so that, and you can see that in this video, if they increase that angle, they're pushing down more molecules per unit time and therefore increasing lift production, okay? The other way they can do it is they increase wing beat frequency. So that's how many times per second they're moving their wings back and forth. So if you imagine doing that faster, you're moving more air down per unit time and therefore increasing lift production. So the two primary ways we think they can do this are that amplitude, that angle through which they beat their wings, and the second is this wing beat frequency. For a host of reasons, which I'm going to try to explain briefly, we tend to think that increasing wing beat frequency is really difficult. They're a special kind of insect. Well, most insects are actually of this kind, which are asynchronous flyers. So they actually don't have direct musculature attached to the wings. So unlike you or I, when we're moving our arms, that's one muscle flexing, right? And our nerves are making that happen. With these insects, the movement of the wings is just based on the flexion of the thorax. And so they have muscles inside the thorax that are oscillating, that are contracting in opposition to each other. That causes the thorax to flex, and really cool joints then cause the wing to move because of that thorax movement, right? That's what allows them to beat their wings 250 times a second. No muscle can actually have nervous impulses quickly enough to flex that many times per second. So it's a passive stretch activated system. So we thought, well, they must be increasing stroke amplitude. So there's an easy way to kind of look at that. So on the left-hand side of this really horrible diagram of a bee, this is what they're doing when you, at the capture elevation, about that 3,200 meters. So that's as far forward as they move their wings, as far back as they move their wings on average. And then the blue is what they do when you get up to above 8,000 meters. So you can see they move their wings further back and they move them further forward on the four strokes. So they're basically increasing that amplitude through which they beat their wings. We can measure stroke amplitude, so that's this one. And we can also measure wing beat frequency, that's the bottom one. And they're not changing wing beat frequency. So that's how many times per second they beat their wings. It's staying the same. They're increasing the amplitude. So again, why might we expect that? I'll show you this video. This is kind of a video trying to show how these thorax work. So here's the wing base. The wings are kind of cut off, but you can see the thorax itself is flexing, and then that's causing the wings to move, okay? And that's activated by vertical muscles that are pulling this way and muscles that are going this way. And both sets of muscles are stretch activated. So when one set of muscles acts, it stretches the other. That causes that set of muscles to flex, which stretches the other, and they go back and forth, okay? Why am I showing you this? Well, it's kind of like a tuning fork. Everybody knows, okay, yeah? So given a certain mass and certain characteristics, if you ring that tuning fork, it's going to give you the same tone. It's going to oscillate at the same frequency. That's how we think these insect thoraxes work. So basically, the structure of the thorax, its musculature, its mass, cause it to oscillate at a certain frequency. It's very difficult and it's very energetically expensive to move it away from that fixed frequency. So we think they don't change wing beat frequency because it's energetically expensive. And we have lots of good data to show you that. I don't have time to go through those data. I'd be happy to talk about that. We can measure metabolic rate and show if they try to change wing beat frequency, it costs them a lot more energy. Okay. So that led an undergrad in my lab to kind of do a side project that ended up being really pretty interesting. So this is Zach Parsons. He's now an environmental consultant, kind of got out of the basic science part. But we had been collecting bees, and I'll show you some data on this in a second, where we go out in the field and we collect queens from different sites, and Lucia's group does this, right? You rear up colonies from those sites. So we can collect bees from a low elevation site. This is in the Western United States, and from a high elevation site at a base of a mountain. We bring those queens into the lab. We rear them in common garden conditions. Everything they experience, the workers, is exactly the same. The only thing that's different between these workers that we're going to talk about is that where their moms came from. Okay, that's the only thing that's different. And what we do is, let me walk you through this before I show that figure. We take these bees, Zach took these bees, workers from these colonies, measured their wing beat frequencies and stroke amplitudes in standard conditions. Now, before I show you this data, you have to realize that the wing beat frequency you expect to have depends in part on your morphology. So if you have a heavier body and smaller wings, right, you can imagine it's moving really fast, right? If you have a smaller body and bigger wings, you don't have to beat them as fast, right? So this relationship between body size and wing size or wing area is called wing loading, okay? So we can account for the individual morphology of the animals by just measuring wing loading. Then we have an expectation of what wing beat frequency will be, and we can compare animals from different locations that have similar morphologies, okay? When Zach did that, we found something really interesting. So this is that wing loading I just mentioned, right? So that's sort of accounting for differences in body size and wing size. These are animals, workers measured that came from low elevation queens. They operate at a fairly high wing beat frequency. Workers from those high elevation queens that have the same wing loadings, in other words, the morphology is identical, operate with lower wing beat frequencies in the exact same conditions. So what we think this is, we're really excited about these data because we think it's the first evidence for local adaptation in flight kinematics. And we think it's about essentially reducing the energetic costs of flight at high elevation. We don't know how it is they maintain flight with reduced wing beat frequencies, even though everything else is the same. And that has to do with really cool subtleties of the way they're flipping their wings and doing cool things with their wings when they're flying. We don't know the answer to that yet. So this is an exciting undergrad project we're following up on. Okay, so hopefully I showed you bees can summit Everest, likely do it by changing stroke amplitude. We might have local adaptation in wing kinematics with wing beat frequency. I will say real quickly that if you're ever in Wyoming or Alabama, we built an Xbox Connect video game that allows you to feel like what it's like to fly like a bee. And so essentially, you know, everybody's played the Connect. It almost doesn't exist anymore, right? But basically there's a sensor. And so you have to flap your wings. It senses you. It can tell the stroke amplitude and your frequency. And then you basically gradually have to visit flowers and climb up in elevation. And so it's great. So, I mean, we've had people from like 4-year-olds up to 80-year-olds play this. And everybody, once they get into it, they completely lose track of their surroundings. You know, doing this, trying to fly, and it gets harder and harder and harder as you get to higher elevation. So it's a fun game. So it's actually, we have installations of that game at a museum at the University of Wyoming and also the University of Alabama. So next, I just want to briefly talk about some thermal tolerance stuff. One of the things that we've been playing with while we've been here. So background, all animals, particularly ectotherms, temperature profoundly affects performance. Right? And performance, by that, I mean how many eggs you lay, how fast you walk, how far you can fly, all of those things, any aspect of performance. And we generally have this curve to describe that, a thermal performance curve. If you get down to really cold temperatures, you can hit critical thermal minimum, which means below this temperature, you no longer function. You sort of pass out. If you get to high enough temperatures, you can hit critical thermal maximum. Too hot, you pass out, right? This has been measured for literally thousands of ectotherms all over the world, lots of latitudes, lots of altitudes. That's all this plot is showing. Critical thermal minimums, maximums. Maximums largely don't seem to change much geographically. We can talk about why that might be. It's kind of an interesting pattern. Minimums do. So as you go from the equator, kind of near where we are, the higher latitudes, either north or south, the temperatures that organisms tend to tolerate get lower and lower. In other words, they're more tolerant of colder and colder temperatures. You see the same pattern across altitude. Get to higher altitudes, which are the lighter colored dots, they can tolerate even colder temperatures, right? So it's a general pattern we see in biology. We know that thermal tolerance changes in response to local conditions. We got very interested in whether or not this was true for alpine bumblebees. And so we first just worked near campus. So our UW, University of Wyoming campus is about 2,200 meters. And that's our low site, because that's what we have. And then we went to the neighboring mountains that are up about 3,300 meters. We collected bees at both sites. This is just an average of air temperatures across those sites that you'd expect. So hopefully you can see the low elevations get hotter, the high elevation sites get colder. That's what you might expect. And then what we did a writing response assay. So this goes back to the 1950s. You take an animal, it's a very simple experiment. You take an animal and you flip it on its back and you ask, can it flip itself back over? And many animals, if they get too hot or too cold, they can no longer flip themselves. And you can imagine if they're in an environment where that happened, they would be food at that point, right? They would be very easy to eat. So this is a writing response assay. And so when we do this and we look at critical thermal maximum, or the maximum temperature they can tolerate, we can see that our red Bombus huntii, those are from low elevation, they can tolerate higher maximum temperatures. And when we look at the cold temperatures, our two high altitude species, these two, blue and purple, can tolerate colder temperatures. And there's a mass effect, and I'll talk a little bit about that later, but the main point is that, oh, this is kind of cool. If we go out and collect bees in the field, we find that alpine bees seem to be more tolerant of cold and maybe less tolerant of heat. But the question is that because they experienced it? If I hang out in cold for long enough, do I acclimate to cold? If I hang out in heat long enough, do I acclimate to heat? In other words, it's not an adaptive trait, it's just an acclimation response. From these data, we can't tell that, right? Because these are just animals we collected in the field. So we wanted to go do something a little different. Now, Clary showed a really nice photo of this bee. This is Bombus vosnesenskii, that is found all across the Western US. It's a great, great bee to work with. So we went to these sites across the Western US to actually ask whether or not these differences in thermal tolerance you see may be due to plasticity or to adaptation. And so to do that, we went to sites either low elevation or high elevation in both California and Oregon, right? And why did we choose these sites? Because they differ in temperatures, right? So the tops of mountains in Oregon are really cold. Low elevation sites in California are quite warm, the red lines, okay? So there's very striking differences in the local climate in these different locations. And that led us to think that the animals should be locally adapted to those temperatures. And so what we did is we caught queens from all of those sites, many queens, brought them into the lab, reared colonies from those queens in common garden conditions. So again, the only thing that's different between these animals is where their moms were from. You guys have probably seen these colonies. This is a Vosnesenskii colony in the lab. You can see the queen up at the top and all the little workers. I think these are pretty good looking bees, as bees go. And then we developed an assay a number of years ago. Whoa. It's really loud. No, it's not. This is an animal. These are animals on a block that were cooling down. And if you watch the one in the middle, she just hit CT min. So they sort of pass out at that cold temperature. And then if you put them back on the bench top, they wake up and go back about their business. So clearly they knock out. It's called chill coma. So it's a loss of neuromuscular function. We do it on the hot end or the cold end, find when they pass out, measure the CT min and max, and from there can ask what they look like. And so when we do this, what we're trying to do again is measure that from workers. I just want to make this clear. These are workers reared from queens. They were reared in the same conditions. Okay, so the only thing that's different is mom. I'm not going to show you any CT max data because it's all the same. They all have the same CT max. It doesn't matter where you get them from. It's always the same. Okay, CT min, cold tolerance, though, very strikingly, right? So these are animals from the tops of mountains in Oregon, very cold climates. They don't pass out until about -7 or -8 degrees C. They're still active. This is not when they stop moving. This is when they actually pass out. So at these temperatures, they're still running around in the vials, okay? Compare that to bees from California. Southern California bees, they pass out up around between 2 and 6, somewhere in there. Okay, so striking differences in cold tolerance across populations. Cold tolerance matches the local climate moms experienced. But I think the key question is, how is it the bees from Mount Hood are able to tolerate 12 degrees C colder temperatures? That's a huge difference, right? We've worked on that. I'm not going to talk about it. So I'm happy to talk about it if you want to. We've done lots of omics to try to figure that out. So metabolomics, transcriptomics, and genomics to figure out what these differences might be. I'm going to end with just a little bit about why we bother measuring these traits. These numbers are probably out of date. Clay might know. It's like now it's like 1 in 4, 25% of North American bumblebee species are worldwide. Oh, Jesus. It's gotten worse. I try to not, bury my head in the sand. Lots of bumblebees are in trouble. It's very well documented in North America and in Europe. It's becoming more documented in other places as well. They're really in trouble. What's I think fascinating about this, there are lots of reasons for this. There's been many reviews about what's happening with this. I think they're a really interesting group in the context of temperature, though, because many people have done cool studies to ask whether or not temperature changes might have something to do with this. This is one of those studies that's really nice. It looks across a bunch of different species and asks whether or not the probability that these animals will occupy spaces on the landscape is increasing or decreasing based on changes in temperature. So increases in temperature are causing decreases in the probability of occupying spots on the landscape. Okay, and you see this for a whole bunch of species. Some species don't seem to be affected. A couple may be going the other direction, okay, because of cooling temperatures. What I think is fascinating about this group, and it's been shown over and over again, is that other factors don't seem to show the same strength of response, right? So if you look at precipitation, if you look at floral resources, you don't see that, right? Temperature seems to be the driver for these guys, and there are multiple studies that have shown that. I'm just going to tell you the point of this figure, and that is that this study has shown that for many North American and European species, the range limits are tightly tied to changes in temperature. Southern range limit is moving northward. Northern range limit is sitting still, right? So they're a cool group because temperature seems to be so important for determining what's going on with populations of these animals. So given that, why measure thermal tolerance? Well, you could imagine measuring heat tolerance is important, because if temperatures are warming, and we know from the physiology, we can do some modeling and say, given the measurements of CT max we have, in red, where do we expect these animals not to be? Because it's too hot. So the black outline here is the actual distribution of Vosnesenskii. The red is the predicted spots where we don't think they should be based on maximum temperatures. And what's cool is that it does a pretty darn good job of selecting out spots we don't expect to see them in the southern hemisphere, right? And if you model that change out, what you see is not good, right? You expect a lot more loss of territory for this animal just based on knowing its CT max, its maximal thermal tolerance. So that's interesting, but it doesn't tell us anything about why the northern range limit isn't moving north. At least the data suggests that for most species, right? So we can look at CT min instead. So I'm going to make 2 points here. One, we often go out and we catch an animal in one location, we measure some physiological trait, and we say that is representative of the species. That's not probably the case, right? So if we assumed that thermal tolerance was based on our California bees, which are the light blue, we would not expect to see them anywhere in the north, right? Because it's too cold for them, right? But there's population variation in thermal tolerance, which means that once you account for the fact that these northern populations actually can tolerate much cooler temperatures, in fact, we do see them up here, right? So that's the first point, right? The second point is that if you look at temperature change, sure, a lot of this stuff is going to get less cold, but if you look at the far north end, there's not much difference expected in the coldest temperatures reached at the north end. They don't move that far north, right? So even though warm summer temperatures may be pushing these animals to move north to escape them, winters may be preventing them from moving north. It's too cold. They can't go further north. It stays cold up there, right? So these basic physiological measures may help us to kind of figure out why it is that these ranges are shifting the way they are in what at first seems kind of non-intuitive, doesn't seem to make sense. So we kind of think that it may be the case that winter cold will kind of prevent escape from summer heat. Okay, so hopefully I convinced you. Again, I didn't talk about any of this, but I'm happy to talk about this if you guys are excited about that later. And I'll say we have a game for this one too. We like making games. This is Bumblebees. It's modeled off World of Warcraft. And you can play it right now, and we encourage you to. It's online. We made this as accessible as possible because we realize not everybody has a Connect. In fact, I don't think anybody has a Connect anymore. And so the idea here is to try to get this idea of the real thing with bumblebees, because at least in the temperate zone, they're seasonal, is you have to put queens out on the landscape, and then you have to direct their workers to go out and forage. And then every winter, you can mess with the traits of your queens. So they can be fuzzier, they can have different ion channels. And then you try again the next year. And the goal is to produce as many queens out of colonies as possible. Okay. So I had a master's student who then took this game to schools all throughout the state of Wyoming to teach these lessons, and then ask actually through pre and post surveys whether or not students actually better understood these. And the good outcome is that they do. In fact, it actually works. And also that middle schoolers can kick anybody's butt on this game. It's crazy. I don't know how they manage. They manage like 20 colonies at once, and they're sending them out. And I'm like, so they get high scores like you wouldn't believe. So that's been fun. So I'll just real quick thank my lab. I've got an awesome lab group. This isn't all of them. This is most of them right now. And funding sources and collaborators. And then of course, you guys. And that's from our field site, or maybe that's from Monserrat. So hopefully there's time for questions. Oh, great.
I think first question I have is, what is the main issue working with bumblebee physiology, and how can you deal with it?
What is the main issue? Behavior. They're smart and they're opinionated. And so they often don't do the experiments the way you want them to. That's probably the biggest challenge. A lot of they're fantastic. And part of the reason I kept working on them, I started working on them and said I was just going to do some stuff and I move on to other things. I've worked with hummingbirds and frogs and other bugs and things, but I keep coming back to bumblebees because you can do amazing things in the lab with them. They're easy to keep in the lab, and then you can do cool experiments. But then you can go into the field and you find them in amazing places all over the world, right? So they're really great group to do sort of paired lab and field studies. They're big enough that you can do a lot of things that are hard to do on things like Drosophila, like fruit flies, right? They're big enough, but they're small enough that you can, again, keep them in the lab. You can do lots of interesting experiments with them with high sample sizes. They're an amazing group. And then, of course, after you work with bumblebees for a little bit, you just love them. I mean, they're amazing animals, right? So, yeah, I think the main challenge really is just behavior. Getting them to do what you want them to do so that you feel like you actually understand the outcome of an experiment. All the other stuff's like logistics and equipment, but that's solvable. That's easy. It's the behavior. Yeah. Yeah. Awesome. Gracias. I don't know how to. I'm going to sign up.
Vamos a dar unos 15 minutos y seguimos con las charlas de los estudiantes. Entonces, no sé si ya están listos porque pues ya.
No. Put you back up there.
changes.
No, o sea, no tengo ¿Qué tipo de? ¿Puedo mandarlo? ¿Por qué me les ayudas a
The round is not as much of a
Do you have any use of it?
Or do you want it in the Google Drive?
Okay. Do you have your mail?
Is it this one? I'm just gonna upload it real quick.
What is the plug?
There is no plug.
There's no plug.
There's no like.
No, for using it? Pero no.
Sammy, ¿qué pasa la casa?
No, it's. But you need to connect with it.
You know a guy.
No, I don't. No, it doesn't work. What? Or do you don't have the email? No. No?
We don't have the email. We don't have Wi-Fi.
Oh my god.
Jeez.
But you can connect that to my.
I have. I'm gonna pop outside and see if the service is a little bit better. Which is like on her hotspot. Okay. I mean, I have
Only PDF.
no PPTX. The PowerPoint.
I can see all
Yeah. I still won't take it out.
Try to get around that
They're always up. It's always up. Because, all of the subject, I'm always shooting blind. Yes. There's like about, yeah. Yeah, like the but I've done it.
Oh yeah, I was hoping we could like pop on a bullet point under the data and says
Yeah.
What email you're gonna send? Because
but I couldn't get onto it.
to this, but I don't know if I can access it. You don't have an email? Because we have or do you don't have this email, or you, or you can send me my email, and I can open my email here. Or
Hey.
Yeah, so like that.
do you have it here? This is different. I have an account. Tell me.
Your hotspot password.
Don't look, guys. Okay, how do I get at? How do I get? It's no. Okay. Oh. Okay. What the fuck?
Mi código es el nombre de mis mascotas.
Oh shit. That's not the right email. I typed my email wrong. No, I typed it in wrong.
The university.
They're gonna see it, but that's okay.
Too much security. Did you have picture?
Okay. And, this doesn't fix Haley's, though. This is only for mine.
Really?
Haley's is different.
Oh my god. You're 100% alone?
Pues son solo.
I'm sorry, were you not working in your class?
Presentar. And let it load.
It's getting there.
Yeah, see, mine, but it should go on a different website because I make it in a different program and I allow it to transfer.
Yeah, and I feel like initially they were.
It's ready.
Mine is good.
Just share.
Yours?
So we can open. No, I think another.
Oh, wait. I'm logged into my email.
Okay.
Porque... Sí. Okay.
You can go out.
Stop. Yep. Stop touching it. Back up. I can't see.
Oh,
Yes. Okay. Where? See?
Presentation. Yours. So Anna, I think
It's in Google Slides.
just tell her to add it to the drive. Because then it will all be able to access it.
If it's just these guys, I'm sure. It's just like.
It is.
Okay, Haley. Is it okay that this is in? Okay, Haley. So there's certain things. This is in Google Slides. Is that okay? And everything looks right?
Sí, súbanlas todas y esperamos un momento.
Perfecto.
Please upload everything, all of the group. Okay. And then,
Oh, well, mine's on a separate website, but I can throw it in there
okay,
later.
that's yeah.
Mine's on this, so I can present from this website.
Okay.
And then throw it in later.
Mm-hmm.
So
Oh, no, that.
here is like
I don't think it's working.
I had to use Sammy's hotspot.
Yeah, I know. And that's why I think Clay had some issue with
Because it doesn't work. Okay. Yeah.
Yeah.
Because this is connected. So Anna, are you uploading it to the drive?
So she said that.
Are you, Anna? Did you upload it into the shared drive? You need to, otherwise you're not going to be able to access it. Yep. Throw it into the IRES shared drive.
Not working? I think so.
But I also just yell. I can be
Well, I mean,
loud.
but that's reality.
No, trust. With my voice.
Just
No.
upload the actual file.
With my voice, it's
Yeah,
loud.
okay.
I'm loud. So you don't want that. Just in the IRES student projects.
So this is one more that I need to be uploaded? Okay.
Dos más.
Yeah.
See, this is why I have mine. Mine is saved on my laptop as a PowerPoint, as a PDF, and it's saved in the
I
website.
know.
Because stuff like this happens all the time.
Mhm.
Yeah. And I have like 4 different versions that are all a little
It's
different.
already-
I like your necklace.
Thank you. Thanks so much. But do you have a lot of photos or why it's so heavy?
Photos.
Photos?
And so this is Adobe, and I take it, and in order to do like this, the drawing on it, it goes into Illustrator. So you download it as a PDF, you throw it into Illustrator, you take it back out as a PDF,
Oh my
and now
God.
it's bigger.
It's
like
like
because there's more.
it's a lot of things.
What?
It's like
No, PPTX.
Yeah.
PPTX, so you can open it in Google Slides.
mhm.
If you do it as a PDF, you're gonna have to scroll like Clay was doing. No, I was talking about something else.
So you're a designer.
Huh?
You're a designer?
Yeah.
Designer? Oh, okay.
I'm a design studies major.
Yeah.
So this is what I do.
It's hard to use Adobe Express or
Adobe Express is easy. It's kind of.
it's like a Canva.
Como Canva, pero more expensive.
Pero
But I was
Mejor o
just Express, no. Pero Illustrator, Photoshop, InDesign.
no, it's better. But it's
But
expensive.
I pay $30 a month.
Really?
Porque I need it for my university.
your
Okay.
university should pay for that.
Yeah.
They pay for, there's like laptops across, or there's not laptops, there's computers on campus that have it for free.
But then you have
But
to stay
you're
on
not.
campus
But
and work on
Your
it.
laptop.
And I work from my iPad and my computer, and I throw it back and forth. So you have to have
You have to pay.
whatever. It's why I work.
Yeah.
Is theirs in there now?
No.
Guys, what
No,
the fuck?
shit.
Y'all. Did you guys put it into this folder?
Well, yeah, it's good.
Okay, so you guys need to turn on your hotspot real quick. It's on?
So do you need internet?
Sammy's might be better. I don't know. Now it's loading? Okay, hold on.
I'm scared that
You guys are stressing me out, dog. I'm so happy there's less people. Because now I can say stupid shit.
Like, it doesn't matter if you're wet.
Yeah.
I don't think it's cold.
Maybe it's not.
Maybe at the highest. Because it's hard, like, if you get water like
That one felt more like a wet.
oh, really?
I was, so there was a little trail.
Yeah.
When I got there, no guy. I'm like, okay, so I like,
Did you go up?
I went through, I was just like going through. I was like, please don't fall in the sinkhole. I was like, but I got to get those 4 hours.
And you found it later.
And I found it later.
Go around the back. Yeah.
We also,
We found it because she had gone that way. That's how you go. You know.
it's nice getting something like that. I don't need to worry about snakes. I don't have.
Exactly. That's true.
But I love wetlands. Wetlands are kind of my favorite. I'm very happy to type this, just because I've grown up in the South. That's the I heard frogs and
Oh, that's awesome.
Is it working? Slowly? Yes! Perfecto.
Yeah.
Yep.
I would agree that's my other favorite.
Because I want to have it preloaded, because if it's preloaded, then we don't have to sit here like this.
I love how big the species are, so you get to the top.
Oh, your pictures are so good.
Yeah.
I like this. You guys did a good job. And that's okay. Okay, so once Anna's gets put in here, I'm going to go use the bathroom. I have to be.
Same speed.
Same speed.
Same speed, but they're being it with that same speed. They're being it through a bigger arc.
I gotta pee. I don't care who goes first, guys. I really, really don't.
Well, we know, there's some of the, we know some of the.
I do like the podium though. Just makes me feel cool. Mary's is in there. Mary and I are the Anna. We're just waiting on Anna.
And it's
It's loading.
finishing. But I think we're gonna start at 1 p.m. I don't know,
At 1?
but
Okay.
maybe at 1 p.m.
Because I gotta go pee.
Yeah.
So that works. That works for me.
My anxiety.
Yeah, I gotta pee it out real quick. No. No.
I mean, the tracheal system.
2 minutes. Jesus. Yeah.
Oh, and Maria, something hotel.
Even though I get
Here, Haley.
I can tell you what
By the airport. Same.
No, don't say.
Okay. Review. So I'm just waiting on. I'm just waiting on you.
I learned that.
Pues si te esperas, vas a tener un puedo acercarte.
Six.
Did you upload her hot sauce?
Vamos a hablar.
Okay, well,
Igual, vamos a poner.
Here, I have her password if you want to use it.
Yeah,
It's like, but.
sí, claro,
Y podemos entonces para enseñar, no estamos hablando.
Sí, bueno, pero tenemos que hablar con Victoria, ¿no? Para ver. Pero todo de vacaciones, fiestas, así que podemos trabajar en diciembre.
No, pero es chévere que vengas a oficina, es muy chévere. Y lo que pasa es que en enero yo no puedo estar, entonces por eso yo le dije a Víctor, entonces que en enero, los primeros días de enero, vuelvo como a finales.
Para mí funciona porque es
En diciembre yo estaba pensando, lo más seguro es el 25 para irme a Costa Rica. Me voy a
también
pegar.
diciembre, ¿no?
Y después de esa semana, pues me voy
Sí, tal vez nos vemos en Costa Rica también, ¿no? Y después aquí.
yo creo, sí. Tengo una invitación para dar la historia, pero necesito mucho más práctica. Con las palabras técnicas es más difícil que yo.
You don't believe it?
No, yeah, it's my place. Pero es similar lo que ocurre con las alas de acá.
Sí.
O sea, lo que estábamos antes.
Yes.
Igual que estás invitado.
Gracias. Pero lo prefiero pasar. Me encanta. Ah,
¿Así?
me gustaría ir.
Sí.
Y ahorita, lo que les estaba contando ahorita, el miércoles tengo una reunión con los de bancos, pues, bancos, como todas las especialidades
aquí en casa, pero es hacia el llano. Entonces, tienen muchas y si hay el convenio, entonces
Sí, eso es bien.
como pan hacia los llanos. O sea, lo que es muy bien.
Y el páramo mañana.
Sí, pero también es diferente. Yo nunca he ido, pero allá me interesa, pero yo tengo una arquitectura, pero está borrado. Puede que ustedes
So many sides of
con nuevos, pero entonces yo quiero hacerles más cosas y tomar fotos. Las fotos ya tengo.
Como los de la charrería, ¿no?
Entonces tengo que mover esas fotos. Que te va a estar molestando para que me des pero quiero que una cámara.
I think what we need to do is have like a 3 or 4 day, in the field seminar.
Yeah, it'd be fun.
We all come and you try. Every night we show our photos and talk about them. Wouldn't that be awesome? Like, try to do this thing, give me your honest opinion. I want to do that, yeah. I wanna do that.
Por favor.
Sí.
Antes del bombo 4.0. Para llevar una buena imagen.
No voy a hablar con ustedes.
No, pasamos con Mike. Por favor, Mike, que no le hablamos.
Y vamos a estar próximamente.
Sí, en Davis.
Davis.
Vamos a pasar en Davis.
Sí, creo que sí. 26. Hay muchos allá, ¿no? Hollis,
Sí, yo sé. Afirmación de
You want me just to go ahead and point it up?
I think so. How do we touch it here?
Oh my god.
Oh,
Sorry.
oh,
You just hit these.
like up and down or side to side?
Side to side.
Okay.
Yep.
Okay.
we used to sketch.
Ready? Listo, so we can go pack? We'll be very fast, we promise. Yeah, you can take pictures if you want. No videos. I don't want to hear my own voice. Oh, Melissa? That's fine, that's fine. Huh?
Pues como para
Are we waiting on Melissa? And saying-
No, I think we'll start now.
Just go?
Sí,
Oh, they're gone?
Buenas tardes, bueno, mi nombre es Víctor González, yo soy profesor de la Universidad de Kansas y también soy uno de los investigadores y docentes que hemos estado aquí 2 meses en el campo de ustedes. Lo que van a ver ahora son uno de los resultados de los proyectos que hicimos aquí en colaboración con el laboratorio de la profesora María Lucía Aguilar y con estudiantes del laboratorio. En total son 5 estudiantes de los Estados Unidos y hemos sido 5 investigadores y docentes de diferentes universidades de Estados Unidos, incluyendo un invitado especial, Ray Ball, que ustedes vieron al comienzo, que participó en todas las actividades durante estas 2 semanas. Estamos muy contentos por la oportunidad de estar aquí, de compartir con algunos de ustedes. Desafortunadamente llegamos en un momento en donde estaban en vacaciones, pero yo sé que hoy es el primer día de clase y estamos sorprendidos de ver tanta gente en el campus, ¿no? Vamos a comenzar con presentaciones cortas de los trabajos que hicimos aquí en el campus y también en diferentes partes de Cundinamarca y Tolima. Tengo la oportunidad de tomar viajes cortos de 2-3 días y tomar muchos datos de diferentes aspectos. Algunos aspectos fisiológicos, otros ecológicos, de comportamiento. Y aquí, bueno, vamos a ver algunos de los trabajos han sido hechos aquí en el bombinario, en el ¿cómo se llama? Bombinario, ¿no?
Sí, en el bombinario.
Sí, que es el que no sé si lo conocen, pero queda a un costado del edificio de biología. Entonces, sí, bienvenidas.
Gracias. Thank you for introducing us. Thank you everyone for coming. And thank you, Malu, for having us. My name is Mary Mitchell.
I'm Ariana Arcuyo.
And we're part of the NSF IRES Columbia. So we're here studying plant-pollinator interactions under drought conditions. And our lead was Luis, I don't know how to say his last name. Duque. Awesome.
Okay. This is our introductory slide. We kind of already said our names, but I am here on your right. I go to Mount Holyoke College, which is in Massachusetts in the United States, but I live in Pennsylvania. And I'm currently a rising sophomore, so I've just finished my first year of college.
I am Marilyn, and I go by Mary Mitchell. I'm from the University of South Carolina. I'm a senior. This is my last semester, and I'm studying biology. All right, so the question we wanted to answer was, will Bombus paluensis make more visits to and spend more time at the flowers of well-watered plants or those under water-stressed conditions?
This is our methods. We are, as Victor said, we're working in the bombinario. We have lights and heat lamps set up to encourage the growth of our plants so that we can reach the flowering stage and do our actual pollinator interaction experiment. So here we have 16 plants total, 8 blueberry and 8 raspberry, which came from the US. There are 4 control per plant species, and there are 4 of our test, which is water stress. One will be watered every week, well watered, and the other one will not be watered since it was planted in the bombinario pots. And then for our actual pollinator observations, we created a large cube out of mesh so that we could observe the bees' interactions with the flowers without interacting with them. And we have a picture of that on the next slide.
So this is what we did. We would set 2 plants inside of here, one well-watered, one watered stressed, and we had a hive in the center. We would sit there and take 3 different observations for about 10 minutes for each observation. Well, exactly 10 minutes each observation. And we wanted to see how many seconds they would go to the flowers, which type of flower they were choosing, and whether they made just an approach, just checking out the flower, or whether they actually visited the flower.
Now, so we encountered a lot of issues, which I'm going to talk about first. And the main one is that the bees did not want to cooperate with our experiment. And though we had a hive in this box and we would close them up overnight so they'd be hungry in the morning, the bees were not interested in our flowers in any way, shape, or form. So often we would sit there for half an hour at a time for our total observation, and we would get maybe 1 bee landing on the flower, maybe none. We had a couple of those. Then we also had issues with our plant growth rate. Because we got them from the US, they were rather small and they had been damaged over shipment. And so rehabilitating them took a long time, especially because both of them are woody species, the blueberries and the raspberries. So we only were really able to begin our pollinator interaction experiments maybe in the last 2 weeks of us being here. And low flower count is also a symptom of that. We only had maybe 2-3 flowers a plant. Often it was 1 flower and 1 flower, so there really weren't a lot of options. And then since this is hopefully a multi-year experiment, we don't have a lot of data, so we haven't done any analysis.
But we have changed the setup of our experiment. We wanted to adapt to the fact that the bees did not like the cube. So the last few observations, we've been sitting with just the plants in the rows and watching every single plant to see if a bee lands. And we've actually got some pretty good data points from that. So, all right, thank you all very much.
Thank
Any
you.
questions?
Let's go. Yeah.
Why did you choose to use plants from the US versus plants?
That's a really great question.
We don't know.
Yeah.
They were given to us.
Yeah. Maybe next year we'll use plants from Colombia.
Yeah. Hopefully. And
Another
then,
question here.
Yeah.
So when you have more data, I mean, are you expecting there's some signal from water stressed plants that indicates somehow to the bees? Like how will the bees know?
Yeah, so potentially they're putting out more nectar, more volatiles from different plants. I'm hoping that in next years we could actually get like a measurement of the volatiles and the nectar amount. But yeah.
So I have a question. Do you know the age of the plants? Like, do they like
No.
any idea?
No.
No, we're lucky that they had the strains written on them.
Yeah. All right.
Everything
Thank you.
good? Thank you. Right. God, I hate this little tiny space. Ooh. Okay, cool. It's got a little bubble on it. Right. My name is Hayasan. I am also with IRES Colombia 2025. And my project focused on stingless bee behavior, specifically their aggression. All right, so about the researchers, this is my mentor, Deb. She was only here for the first 3 weeks, so she's not here today. But she is a professor and researcher at Kansas University. She actually studies molecular systematics along with social arthropods, specifically spiders and bees. And then I am an undergraduate student at North Carolina State University. I am a senior, and I actually study design, but I minored in entomology and international studies. All right, so what are we doing? So when we think of bee nest defense, usually we think of you're going to get stung, right? You know, we're all used to the honeybee stings, the bumblebee stings. They kind of swell up, they get red, all of that kind of stuff. Well, stingless bees, like the name suggests, don't sting. They actually bite you. And they're very, very small. And so for our research, we were super curious about, you know, what are the different behaviors and defense behaviors of these stingless bees because they bite. And we want to look and see how aggressive are these various species of stingless bees. And we also want to see if they exhibit what's called suicidal biting behavior. So some species of these bees have shown to bite and then they can't let go. And so when you go to pull them off, you actually lose their head and their head stays on you, which is not super comfortable. And so in our research, we're just kind of exploring the different defense behavior and the differing aggression levels across species, specifically in Colombia. So this is all based off of a study that comes out of Brazil, where they looked at, I think they did tests over 300 different like flag nests and things like that. So they have a bunch of different species. Our little group is not quite as big as theirs, but this is a multi-year project, so we're hoping to continue to expand. Get a couple more different species from Colombia because it's very diverse here. And so this study is pretty much our study is based off of this study. And so in it, they look at, you know, aggression behavior, suicidal behavior. They also look at the mandible size to see if their mouth size and characteristics correlate with their aggression levels and the likelihood of suicidal biting. And something that they did that we're probably not going to do is a ranking scale of how bad do the bites hurt. I'm not a fan of pain, so I'm not going to do that. I didn't think any of the other students would be a fan either, so we kind of skipped that part. So these are the various sites that we looked at. So we checked out Campo Colombia, which is one of the previous photos, and it is a very cool place to visit. They have multiple species of bees. They have both wild and managed hives, and they have rescued hives. So you can find hives of all these different species, and you can find them in trees. You can find them in boxes. You can even find them in the bottom of a boot. Our other site, where we found the Parfumura zonada, is going to be Chacake, which was super cool. Those were all wild nests, all found by Ariana because she's awesome and really good at finding these stingless bee nests. And then our final site was in Ambolema. And so we have a mix of both wild nests that we found in a forest nearby, and then also managed nests at a friend's house that happen to have quite a few boxes of a couple of these species. And they all have extremely different behaviors. So this is sort of the process that we were using to test the aggression. So you see, first thing we do is we find the nest. Sometimes it's easier than others. You know, finding the managed nest is pretty easy. People can tell you where they are. The wild nest, Ariana definitely did most of the hunting for us.
And so you find the nest. Okay, well, what do you do now? All right, so you're gonna write down, is it in a box? Is it in a tree? What color is it? How many bees do you see? Does it seem like it might be aggressive? Okay, great. So now you're gonna take a photo. And then in that photo, you can see, are the bees flying around? Are there guard bees? If there are guard bees, how many? And are they facing out looking at you? Are they facing each other? Are they in a little ring in a circle? And that helps you look at the behavior as well. So we take a photograph, we have a number so that we can figure out, which nest is which. And we have these protective hats just in case they are an aggressive nest. Most of the nests that we dealt with were not. And then we're going to record all of our observations. So you're looking at temperature, hive, is it wild, those kinds of things, because there's a variety of things that can impact the behavior of these stingless bees and bees in general. The second part is kind of the fun part. So what we do is we take this little black flag and we put it on a stick. The black is helpful because it helps the bees think it's an intruder. So we kind of go and we just make them mad. So you start with the flag very close to the nest. You wiggle it just a little bit. And then after a minute, you see if they bite. If they didn't, it's the end of the study. They're not aggressive. If they do bite, you slowly back up and you count how many seconds until they stop biting. So you can see the attack latency. And then, so that's where we're moving the flag away. Do the bees follow? How many bees? How long? And that helps you quantify the aggression levels. And then at the end, you count how many are on the flag. This is one of our more aggressive species. And so on here, you can see we have a lot of biters. You go and you count how many are on the flag originally. Then you go and you brush them off just to make sure they're not suicidal or anything. And if they come off, they come off. You do another count. And then you take your fingers, because most of these species are not very mean, and you pull them off. And a majority of the time, the bees actually come off. Every so often, we would have one that would stay. And if it stays and it falls off and it's dead, or its head stays on the flag or anything like that, that means it has suicidal biting behavior. So this is super preliminary data. We did a test of at least 8 different species across 30 different nests. So our sample size is pretty small compared to the other study, but what we found is these are really the only 2 species that have suicidal biting tendencies. We have about 6 that showed biting tendencies, and then of those 6, 2 actually bit. And you can see it varies across all the different nests. And so some of them can be quite aggressive. So these are our more aggressive species, but they're really not suicidal, which is really interesting compared to a lot of the species that come out of the Brazil study. So results so far, this is a continuous project. So this is something that we're going to continue to look at. Next year, we want to continue to look at those mandible sizes. We want to test a couple more species and expand, the amount of nests that we can get. So we're still conducting the testing, but according to preliminary data, we found that most of the species here do not exhibit suicidal behavior, and they're not aggressive. Of the tested species, the 2 that were the most aggressive and showed any sign of suicidal behavior was the Scapta trigona and the Paraparthopona. So these are just some examples. These are what the bees look like close up, and this is an example of a wild nest versus a managed nest, and they do look a little bit different. So this is a study that we were comparing it to. And that's it.
That's really cool. So I'm wondering about variation among nests. Does the size of the nest or the location of the nest affect their tendencies?
From what we were finding, not really. So managed versus wild hives had about the same. We did find, so the one species that we were studying, that did vary between Colombia and Brazil. So the Brazilian ones were a lot more aggressive, but that's not an because we had a little bit more time. But they were a lot more aggressive in Brazil than they were here in Colombia. So that would be another question that we would go back and look at. Okay, is it a temperature difference that can make them more aggressive? Are there more, predators in Brazil than there are here in Colombia that makes them more aggressive? Is it the time of day? So that's something that we can continue to expand for next year, that we could develop another project that would, ask a couple more questions.
So so when you look at your project in isolation, it is isolated from the other topics that we are going to be discussing here in terms of climate change, right? And global warming in general. How would you suggest that we can link this your project in terms of the behavior of stingless bees and the global warming, or how temperature might be affecting your results. I want you to explore a little bit of that.
Mm-hmm. So it could be a really good question. We could, take a lot of these species and mix it with a lot of the other projects that we were doing, so the CT Min and the CT Maps. And then also the project that we just did this past weekend where we were looking at the behavior levels and seeing, does temperature have an effect over time versus specific temperature in a short amount of time and things like that, because these are very small. And like we were finding them in very specific areas, so not really near a ton of cities. And we found more managed ones than we did find wild ones. At this point, it's been a little bit easier to use those. So I think next year, specifically trying to look at where the locations of the wild ones could be interesting, and then we could use that and see if it correlates with any temperature data.
So you're saying, like, if, for instance, if it is too cold or too hot, the aggressive behavior or suicidal behavior might be impacting on how?
So with time of day, with climate, things like that. I mean, that's something that could have been the difference between Colombia and Brazil. We don't know the temperature exactly where they were doing the study, because it was at the university over a year. Versus like here, we had a couple different places, and we have some temperature data, but it's hard to compare it to the other city.
Buenos días, hoy yo usaré Spanglish y mi proyecto es biodiversidad y distribución de bombas a través de gradientes de elevación en Cundinamarca, Colombia. Y primero, sobre mí, me llamo Haley Bates y soy del estado de Nebraska y soy un estudiante de la Universidad Nebraska en Omaha. Yo estudio biología y español con un minor en sostenibilidad y mis principales focos son en restauración ambiental, conservación y la resiliencia climática de especies vulnerables y sus hábitats. Algunos contextos para bombas en Colombia. Bombas es el género de abejas. El nombre común es abejorros. Colombia tiene 9 especies de bombas y estos aquí. Y la estrella significa que fueron recogidos en este estudio. Entonces, tengo 5 de 9 especies. Y la historia natural de bombas. Las especies de bombas son muy importantes polinizadores en ecosistemas frágiles y amenazados. Somos los páramos y los bosques de nubes en Colombia. También estos ecosistemas son muy importantes para agua en Colombia y para los sistemas de agua en Colombia. Bombas ayuda al mantenimiento de biodiversidad de plantas. Entonces, la biodiversidad de plantas, mantenimiento sistemas de agua limpia. Y eso es muy, muy importante por la población de gente en Colombia. Bombas es importante para cultivos también, especialmente los cultivos de papa y maracuya. Y para papa es un principal fuente de ingresos y seguridad alimentaria para más de 100,000 familias en Colombia. Y los objetivos de este proyecto, la hipótesis fue cambio climático tiene un impacto en nosotros la distribución y abundancia de bombas especies a través de las elevaciones en Colombia. Y somos a recoger los individuos de bombas en los sitios con diferentes elevaciones y comparar la distribución de especies a las poblaciones de bombas de un estudio en los 80s de Dr. Rodolfo Espiña de la Universidad Nacional de Colombia. Y entonces comparar la longitud de las alas, la longitud del cuerpo y la distancia intertegular. Y para las especies paloenses, los patrones de color, porque en paloenses tienen muchos diferentes patrones de color. Y los meteros se recolectan los individuos de bombas de cada sitio durante un periodo, es aproximadamente una hora, depende en la clima, especialmente la lluvia, y se registran los longitud de cuerpo. Y este es un mapa de mis sitios. Solo tengo solo 5 para este año. Y los resultados. Este es un gráfico de distribución altitudinal de los abejorros en los Andes para los 80s y los colores por cada especie y el tipo de hábitat. Y tienen la distribución altitudinal para ahora, este verano. Es obvio, necesitamos más tipos de hábitat. Y esta es una comparación entre los gráficos. Distribución altitudinal. Este gráfico es la misma información de el otro, pero por especies. Y los colores por los hábitats. Y este es de este verano. La conclusión preliminar. Montaña habitat descendiendo en biodiversidad, 80 especies en los 80, 8 especies en los 80s y solo 3 especies en 2025. Y para montaña bajo es el mismo caso, 6 especies en los 80s y solo 1 en 2025. Y se observó que la bandida de rubicondes aumentaba en los hábitats montaña y es posible que rubicondes puede estar superando otras especies en elevación. Y también es el caso similar para Excellence. Excellence fue muy raro en el pasado y este año es muy común, especialmente en Chicaque. También se observa en tasas más altas, en elevaciones más altas, de que el pasado. Esta podría seguir mejor aptitud de Excellence en respuesta al cambio climático. Y las limitaciones y áreas de investigación adicional. Obvio, necesitamos más sitios y más colecciones. Es sentarse en sitios tropicales, primapanzosos, subandios y andios para llenar los huecos en la investigación. Y las preguntas para continuación, ¿cómo se ha visto afecta la polinización de las plantas por el cambio en las poblaciones de polinizadores? ¿Es importante la tipo de especies para las plantas o no? ¿Y qué hábitats de abejorros son mejor preocupación para los esfuerzos de conservación y restauración? Y se puede aprovechar los microclimas y las comunidades de plantas para aumentar la resiliencia climática de poblaciones de abejorros. Pienso que these are the most important to me because I'm someone who deeply cares about conservation, and I think that needs to be our main focus going forward. So how we change how we focus on land depending on what we know about projections. So if you were here for Michael's talk, they have projections about where we think bumblebees are going to be in the future. So using those predictions to actually figure out what type of land we need to prioritize for conservation restoration efforts. And I think it's really awesome to have the projections, but if we're not doing anything about it or using that information for conservation, I don't think we're really doing these bees the service that they deserve. And also, I think microclimates are this thing that we really need to break into and look at. So even though we might be having critical thermal limits that are changing the way that bumblebees are distributed, is that actually something that we can offset with microclimates on farms? Can we actually provide these bees like safe havens in order to improve their climate resiliency and the climate resiliency of habitats. So those are two things that I'm really interested in seeing for their studies, because I know this is a 3-year project look at, and also just improving our sample size. Pero muchas gracias para todas las personas y las organizaciones para la apoyo en este proyecto. Gracias. ¿Preguntas?
That's great. Does the Ospina study have body sizes, or are you measuring body sizes from collections?
So we actually went back and studied, and we did the measurements for every single bee that he collected during that 80s collection period. So Mary and Anna were both really putting in the work with the calibers, and I think we ended up measuring over 400 bees.
Nice. And then do you have predictions for how that will change?
We're not really sure. We were kind of interested to see are the body sizes getting bigger in order to deal with different thermal ecosystems? Like as they're going up, are they getting bigger bodies in order to stay warmer? Or do they need to get smaller in order to go into warmer places where they can offload that heat quicker? So that's kind of what we're looking at with that. We haven't actually done the analysis yet, but I'm really excited to see if there's any difference. Or even like for excellence, where we didn't see a lot of excellence, as they're moving up and kind of becoming a bigger competitor, is their body size reflecting that due to a lack of competition? I don't know.
One thing that might be interesting to look at as well is the furriness of the bumblebees, if that's changed at all. Because like one thing I noticed looking at those photos of transversalis is they've got longer bodies and greatly reduced hair, basically, seeping on their bodies. So it'd be interesting.
Yeah. Or even like the patterns, if we're seeing like an abundance of different patterns across time for the Paloensis, and if that's actually like an advantage for them, I think is really interesting. Yeah. Anyone else?
Yeah, I like the questions that you pose at the end of the your talk, and from what you have seen so far, you had the opportunity to visit several sites, collect them, and the microclimate is something that I know Michael is very interested in that too. Like and from what we have seen and experienced here, it's not the same when it's raining and you just move up a little bit and a little bit of sunshine, it changes completely what you are experiencing. For bees might be totally different. And from what I'm trying to ask you, like from your experience, what predictions can you make, or what do you think this is going to from the different species that you have collected? If you have any.
Yeah, so I think definitely visiting Zipa with Michael and looking at the difference in the activity between Hortulanus and Paloensis. The Hortulanus, they did not care about the rain. They kept flying, and seeing how the Paloensis were a lot less likely to come out of that nest. I think you're looking at species difference in that site alone. And it could just be like individual nest behaviors, but definitely it seemed like the Hortulanus were more hardy. And I think even like at La Montaña del Oso, like seeing how the Hortulanus like kind of hunker down on the grass, especially the males when it's raining, and then you see them get active as soon as it's not. Like what difference would it make if we had more places for them to kind of hunker down and wait for that sun to come out? Because that's the thing with the paramos, like it's raining 1 minute and then it's full sun the next. So that makes a huge difference for a bee, and can be the difference of maybe they did reach their critical thermal minimum, but then the sun comes out and they're active again because they're able to warm up. So yeah, I think it'll be really interesting. Anything else?
¿Quieres iniciar? ¿Listo? Ok.
Buenos días para todos. Hoy les vamos a hablar acerca de observaciones de características fisiológicas en bombus, en el género bombus, perteneciente al orden Hymenoptera y la familia Apidae. Más estas características fisiológicas están enfocadas en tres valores importantes, o en tres conceptos importantes. Uno es acerca de lo que vendrá siendo los valores termales críticos, ya sea el mínimo, valor mínimo o el valor máximo, y acerca de un tema muy importante que es la desecación.
Okay. Hola, me llamo Ana. Voy a hablar en español un poquito y voy a empezar con tolerancia térmica, mi parte del proyecto. Hay conceptos importantes sobre diversidad de abejas y el efecto de cambio climático en plantas y polinizadores. Objetivo y enfoque de tolerancia térmica, métodos, resultados preliminares y referencias. Primero, hay mucha biodiversidad de abejas en el mundo. Hay diferencias en tamaño, como pequeño o grande, forma, color, velocidad, como mucho pelo o nada, tiempo de forajeo, anidación, sociabilidad y más. El cambio climático impacta la temperatura, primero, y desecación. Voy a enfocar en temperatura primero. Las interacciones entre la planta y el polinizador son bastante sensibles. Con temperaturas altas, las plantas y abejas son afectados del clima. Las abejas toleran diferentes temperaturas por diferentes periodos de tiempo y la temperatura óptima de actividad depende de la especie de abeja y del individuo. Unas abejas viven más en temperaturas altas y otras en temperaturas bajas. La pregunta más importante para mi parte del proyecto es cuál es el efecto de la edad en la termotolerancia de las abejas. Usamos la especie Bombus valuensis de una clínica en Santa Rosa, en la ciudad de Bogotá. Hay muchas abejas allí. Y usamos 7 estados de vida, 3 de larvas, larva 1, 2, 3, prepupa, pupa, nuevo adulto y adulto. Y 5 individuos de cada uno. Primero colectamos individuos de cada edad, 5, y luego colocamos en un vial con algodón y una gota de agua por humedad. Y tercero, iniciamos CT Max para aumentar la temperatura y observar el comportamiento de la... pero ponemos las abejas en el plato y aumentar la temperatura para CT Max. Nuestros resultados son las larvas y adultos pueden tolerar más temperatura, más alta, y las pupas no toleran temperatura alta mucho. Y yo busqué una otra papel científica con creo que es apis mellifera, abejas de miel, Y las reinas pueden tolerar más temperatura alta que larva. Es muy interesante porque nuestros resultados son diferentes, pero es interesante para el futuro. Y en el futuro quiero usar más abejas y más especies de abejas porque hay mucho más para aprender sobre CTMAX y edades de abejas.
Bueno, pues ahora en la segunda parte, que va a ser la parte de desecación, vamos a tener unos conceptos importantes, un poco una introducción de las especies de abejorros que encontramos en esta zona de Cundinamarca, que es la desecación y otras ideas claves, la importancia del estudio, su aplicabilidad, los métodos, los resultados preliminares y pues las posibles propuestas. Y también las referencias. Entonces, una introducción un poco a los abejorros. Vamos a encontrar aproximadamente estas 5 especies de bombus, donde pues en la tabla de la esquina podemos encontrar aproximadamente a qué altitud se encuentran estos.
Ok, bueno. En la pasada tabla se resaltaba que nosotros, digamos, hay una amplia distribución de los abejorros, teniendo abejorros que pasan los 3.600 metros sobre el nivel del mar, como es el caso de Bombus funebris, abejorros que son un poco más generalistas en su ambiente, como es Bombus pauloensis. Cabe aclarar que estas investigaciones, pues ya algunas tienen sus años, no hay como investigaciones muy nuevas, muy nuevas acerca de esto. Pero, por ejemplo, tenemos especies generalistas como lo es nuestro Bombus pauloensis, que es el que tenemos acá en la universidad, con una distribución desde los 150 metros hasta los 3.500 metros sobre el nivel del mar. ¿Por qué es importante? Porque la altitud influye significativamente en las adaptaciones que estos presentan. Y al influir significativamente en las adaptaciones que estos presentan, pues genera diferentes respuestas. Estas respuestas pueden ser la tolerancia al frío, una eficiencia metabólica mayor, entre otras. ¿Por qué es importante y por qué es necesario saber esto? Porque nosotros estamos viviendo, pues estamos pasando por un proceso de cambio climático, que pues en otras palabras se puede traducir como un aumento de temperaturas y pues humedades más bajas. ¿Esto a qué lleva? Lleva a que esto provoca una pérdida de agua, especialmente en insectos terrestres, y estos organismos, los insectos, pues al ser ectotermos, y también ellos están muy correlacionados con las condiciones ambientales. Entonces, si estas cambian un poco, ellos se ven afectados, por lo cual es un desafío que ellos deben afrontar. Ahora, el concepto de desecación. No sé si para algunos sea nuevo, pero es como la eliminación excesiva de agua que afecta o interfiere el equilibrio interno del insecto, la homeostasis. Entonces, ¿cómo podemos medir esto? Se puede medir por el contenido crítico de agua, la tasa de pérdida de agua y el tiempo de supervivencia en condiciones secas, que eso fue lo que nosotros realizamos. Entonces,
que una parte en la importancia de aplicabilidad es, esto nos permite determinar la vulnerabilidad fisiológica a la pérdida de agua. Esto claramente enfocado en los cambios que estamos presentando debido al cambio climático y nos permite así como hacer enfoques a nivel de conservación y cuidado de las diferentes especies dependiendo de qué tan rápido son afectados por las temperaturas y la baja tasa de humedad que presentan.
Bueno, entonces, para cumplir este objetivo, primero debemos construir cámaras de desecación, que son las que se observan en la parte derecha de ustedes. Entonces, ¿qué es lo primero? Pues la tapa de cada tubo Falcon se le realizaron pues unos agujeros de 1 centímetro de diámetro, se unieron 2 viales entre sí, como se puede ver en la imagen, asegurando que estuvieran alineados los orificios y en medio de ellos iba una malla. ¿Para qué se aseguraba que estuvieran alineados entre sí? Para que hubiera un buen flujo de aire a través de la cámara que contenía el desecante y pues donde iba a estar el abejorro. Se sellaron las tapas con cinta y parafín y pues finalmente se agregó un trozo de algodón en la parte donde iba a estar el abejorro para que no estuviera en contacto directo. Ahora, el proceso de medición de pérdida de agua. Entonces, primero se debieron colectar los abejorros. Estos fueron recolectados en diferentes ubicaciones altitudinales, dependiendo pues de su distribución. fueron alimentados con una gota de néctar, que era solución 1:1 de agua y azúcar. Tuvimos un pesaje inicial para saber exactamente cuál es la masa fresca inicial. Y pues inició el proceso de secación. Entonces los abejorros se colocaron en las cámaras y ya se inició a ver el proceso de pérdida de agua. Cada 2 horas los abejorros eran pesados nuevamente para así poder obtener nuestra tasa de pérdida de agua, y finalmente cuando el abejorro murió, pues se determina la masa fresca muerta.
Ya la parte un poco de cómo se determinó el porcentaje de pérdida de agua, pues ya los individuos que habían muerto se pusieron como una especie de cajita o barquitos de papel aluminio, y estos pues se iniciaron un proceso de secado en un horno. El proceso duró a 70 grados durante 24 horas, después de esto se hacía un pesaje, después se volvían a introducir en el horno y se repetía este mismo proceso durante 72 horas para al final poder determinar cuál era el contenido de agua. Y pues los porcentajes que se manejaban era el porcentaje de pérdida de agua, que era la pérdida de agua más la masa fresca inicial por 100, la tasa de pérdida de agua, que era la pérdida de agua más masa dividida en la masa fresca inicial, sobre la duración, esto multiplicado por 100, y el contenido crítico de agua, que era la masa fresca inicial, menos la masa fresca dividido en masa fresca inicial por 100.
Ok, bueno, los resultados preliminares. ¿Qué es importante resaltar de acá? Primero, que en la duración total que los bombos duraron dentro del vial, el número mayor, la duración total mayor, fue para Bombus pauloensis, casi duplicando a las otras especies. Entonces ahí surgen preguntas como esto estará relacionado con su distribución altitudinal. En temas de pérdida de agua encontramos los mismos resultados, casi los mismos valores entre sí. En el porcentaje de pérdida de agua encontramos pues, que es un poco menor con relación al cuerpo en Bombus funebris, y en la tasa de pérdida de agua, que es otro resultado importante a resaltar, es Bombus rubicundus, que es un bombus que se ubica en altitudes altas. Encontramos que tiene una tasa de pérdida de agua casi el doble que las otras. Entonces es otro resultado importante. Y en contenido crítico de agua, que es el contenido de agua que ellos poseen justo cuando fallecen, que ellos no perdieron en la cámara de secación, encontramos un porcentaje similar entre sí.
Un poco en las nuevas propuestas, se quiere determinar la pérdida de agua a partir de la cutícula. Los insectos, en especial pues los bombus, su capa protectora, su primera barrera, digamos, para evitar esa pérdida de agua es su cutícula, aunque también la pueden perder por pues sus desechos y por la boca por donde ingieren su comida. Entonces, en este caso hicimos un preliminar con 4 individuos colectados acá en la universidad, en donde para asegurarnos que la pérdida de agua sea por la cutícula, lo que hicimos fue taparle con silicona el ano y quitarles la mandíbula y tapárselas también ese espacio con silicona, claramente después de haber sacrificado a los 4 individuos. También, antes de iniciar el proceso, se aseguró que no tuvieran alimento en su interior, entonces se les presionó el abdomen como para que vomitaran la comida si tenían comida. Y pues aproximadamente después se realizó el pesado de los individuos, y después de haber hecho el procedimiento de quitar la mandíbula, se pesó durante cada hora hasta un punto donde se estabilizara el peso. Y eso duró aproximadamente 5 horas en los individuos que hicimos ese preliminar. Pues ya estas son un poco las referencias que trabajamos. Gracias.
Gracias. ¿Preguntas?
Sí.
The values, this is really neat, cool stuff. So the values for CT max are quite high. How do you measure CT max of a pupa?
Observamos el movimiento del cuerpo y la cabeza, y en las larvas solo podemos mirar la cabeza, el movimiento de la cabeza, un poquito, sí. Pero es difícil.
Sí, para que de mover.
Mhm.
One more question. Sorry. Do you think there might be an interaction between desiccation and heat?
¿Quieres hacerlo tú?
Sí.
Mira.
Okay. In English. I think so. I think depending on the characteristics of the bee, it does depend. So, like, I think body size and the amount of hair that the bee has definitely, we have looked into in the past, definitely play a role in heat, like how much heat it can retain or lose. And same thing with water loss. We found an article with ants showing that ants with more hair retained more water in their body because the hair serves as like a protective layer. But between heat and water loss, I'm not sure. It's a good thing to think about.
Los datos preliminares muestran que hay diferencias en las diferentes especies, ¿cierto? Y cómo, de lo que saben, cómo se relacionan estos datos con lo que conocen de la biología o también de las predicciones que Hailey mencionó sobre microclima y esas cosas, ¿cómo creen que puede estar relacionado?
Ok, por ejemplo, en el caso de Bombus rubicundus, nosotros, pues, como se observa, la tasa de pérdida de agua es mayor comparada con las otras. Entonces, ¿qué pasa? Esta tasa de pérdida de agua puede estar está muy relacionada con la temperatura. Entonces, a temperaturas, este es un bombus que está ubicado muy cerca a la franja, o sea, del círculo, la línea de árboles, ya en límites con páramo y se ubica en zonas de páramo. Entonces, ¿qué pasa? Al aumentar las temperaturas puede que, por ejemplo, esta especie se vea más afectada por la tasa de pérdida de agua tan alta que tiene. En cambio, pues hay otros como, por ejemplo, acá faltan resultados que no se han procesado aún acerca de Bombus excellens y Bombus hortulanus, que también, pues uno, como lo mencionaban anteriormente, pues él ya, digamos que su abundancia en Bombus excellens ha aumentado. Entonces puede ser que él en temas de tasa de pérdida de agua o en otros aspectos acerca de la desecación o del City Max y City Min sea más resiliente a los cambios climáticos.
También puedes entender que la zona donde está Rubicundus también es una zona de alta humedad. Entonces eso también le ayuda en su proceso, mientras que a los aspectos de cambio climático, altas temperaturas y baja humedad, pues claramente va a perder un poco más de agua porque se va a ver bastante afectado.
Gracias.
Tengo una curiosidad, pero ¿y si la diferencia se encuentra a nivel de cutícula?
También.
Porque pues si la fisiología es
Cada individuo está, también
no
puede
ser
ser.
tanto por la temperatura, sino por la estructura propia de la cutícula.
Sí, para eso pues también sería lo ideal hacerlo con diferentes individuos de las diferentes especies y determinar si realmente hay una diferencia entre la cutícula.
¿No?
Gracias.
Gracias.
Entonces, con esto finalizamos. Pues creo que no sé si quieres dar unas palabras.
Sí, no, pues quiero finalizar diciéndole gracias a todos los que están aquí presentes hoy, a los estudiantes. Si están interesados en abejas, por favor comuníquense con ellas. Este programa es financiado por la Fundación Nacional de Ciencias de los Estados Unidos y este primer año es una continuación de un programa que comenzó hace 3 años, 4 años.
Sí, 4 años.
4 años, y vamos a venir aquí los próximos 2 años. O sea que si están interesados ustedes en cosas parecidas, y bueno, y otras, aquí estaremos el próximo año, junio y julio. Pues contentos, agradecerles también a los estudiantes de maestría, doctorado de laboratorio, los estudiantes de pregrado que participaron en esta experiencia. Obviamente los estudiantes que trajimos de Estados Unidos, los 5 estudiantes que presentaron, que en las últimas 2 semanas, bajo la dirección del profesor Michael, trabajaron muy duro para tener todos estos datos de fisiología y tratar de tener una visión muy general como usted se ha podido dar cuenta, de lo que está pasando con estos insectos y polinizadores, ¿no? No es solamente la fisiología o la ecología, sino también comportamiento y pensar también las aplicaciones, que eso fue lo que me pareció muy importante que él trató de poner aquí y se vio en las otras charlas, ¿no? Que la conservación y entender de esto de una manera aplicada para qué nos sirve la ciencia en nuestro país y en general en el mundo es clave, ¿no? O sea, porque al final los que hacemos ciencia lo hacemos porque queremos que este mundo sea mejor y poder aplicar los conocimientos para mejorar y proteger la naturaleza. También, bueno, finalmente, gracias a María Lucía, Michael, Megan por estar aquí y Claire. Ha sido muy, muy chévere esa experiencia y espero que no sea la última, ¿no? Que nos veamos más. Y bueno, muchas gracias.
Entonces, les agradezco mucho por haber participado en las charlas de los chicos, pues para que ustedes conocieran un poco todo lo que hicieron en vacaciones, porque aquí pues ustedes se dieron cuenta que también están estudiantes pues de la universidad y que hay oportunidades ahí. Entonces, pues les agradezco mucho a los que participaron y pues ya, entonces con esto ya finalizamos. Nos vemos entonces ahorita en el combinado. Melissa se van dirigiendo para allá. Y yo me quedo un momentico con los de TG2, por favor. Y los demás, muchas gracias por todo.
Should have known. Okay, I think we should go down to the seminary. I think they have something for us.
Bueno, chicos, hoy vamos a hacer mucho.